So again, okay. So okay, I'm seeing no questions or no comments. So we move on to the lecture. And again, another default question: can you hear me and can you see the screen? Okay, brilliant. So as you see, before we move on to the lecture, I thought I would like to point out some topic that might be of interest to you, namely as the Polish Association of IEEE Antenna and Propagation Society. We've been organizing actually a series of invited webinars, which are, well, typically they are made by quite well-recognized professors from all around the world. So hopefully the IEEE should by now recognize also as an organization which stands behind many of the telecommunication standards. But of course, as part of the standardization and legal framework, they are also responsible for many more, including scientific research in terms of journals, as well as some educational. And just to point out here at the very bottom, sorry, okay. So the next webinar will be on the 12th of May at exactly at noon. Will be given by Professor Oskar Quevedo Terul from the KTH Royal Institute of Technology in Sweden, and he'll be talking a little bit about lens antennas. This is, of course, mainly from the point of view of millimeter wave communication and the research that he is conducting. With also some optical overtones, so to speak. So it's of course no obligation to attend, but if you found that might be something interesting for you, feel free to register under the link over here, and I'll basically put this flyer in the files section on the Microsoft Teams so that you could browse and see what's happening. So unfortunately, this will be the last lecture for the spring series. However, we are planning to organize some more in autumn later this year. Okay, so that was just some announcement, and now we move on to our usual content. So okay, right. So just to wrap up a little bit, last week, again, we've been talking about the link budget, which is basically the calculation of wireless radio telecommunication system. And basically it tells us how much power we will get at a certain distance between transmitter and receive antenna given different constraints and different components of the system. And of course, it is used to calculate the power at a certain distance, but in most cases, we would actually use it to engineer the telecommunication system. So basically, the minimum power will be given by the sensitivity of the receiver, as is the case over here, right? And we want to see what, for example, antenna gain we need to have efficient communication over that distance. And this is basically it's actually very simple, but very fundamental equation for the wireless telecommunication. And again, it's actually very modular. So it's quite interesting not only to be able to calculate the numbers, which, using logarithm and decibel scales is simple addition, so quite straightforward, or it should be. However, it is modular in the sense that, if you experience any additional losses in your system or any additional amplification, it is basically straightforward to add different components into the equation either with the plus sign, so multiplication if it's improvement in your signal strength, your signal power, or if it's attenuation with the minus sign, which corresponds to, of course, division in the logarithmic case. So again, it's quite important where this equation comes from. And then equivalent isotropically radiated power. This is actually a small subcomponent of. So this is basically just. Well, let's just say these two components put together with some cable loss potentially. So this is like a fraction of the link budget, but this is also important. So equivalently isotropically radiated power, simply because this parameter is used for many framework standards and also legal aspects, right? So it's simply important to understand how what it means. And then also some, well, generic term about antennas. And basically what I would like to repeat with this slide is that, you should be aware of the distinction between the near field and the far field of the antenna. In the sense that most of the parameter we talked at this lecture, the classical parameters, they are defined with respect to the far field. However, you should be aware that the far field means we are operating at a significant distance from your antenna. And basically, significant distance means that we can calculate all the equations, assuming antenna as a point source, which generates basically spherical waves that propagate outside of our antenna. If we go to the near field, those spherical source is not anymore spherical source, but obviously with certain radiation pattern, right? So we assume antenna is a point, but of course we don't assume it radiates isotropically. We know radiation pattern now. And of course, when we move closer to the antenna, this is not anymore the case. For example, different components of our antenna can have some different interference as a function of if you move to the near field. And most importantly, if you go to the reactive near field, well, the generic rule is that everything that is close enough to your antenna may effectively become part of your antenna. Okay, so and this is basically well, to illustrate the problem maybe better, if you basically think about the coil, simple curly wire which is there, and of course it will act as a wire, right? But just because I'm not saying this is of course not an antenna yet, but because it generates some magnetic field, it's source energy as a magnetic field surrounding that coil, and hopefully that should be clear that if you put another coil very close to that coil, it simply changes its function just by the proximity, right? That's suddenly out of a single coil, it becomes a transformer. And with antenna, it is it may be similar. I mean, more complicated, but it's pretty much the same thing, right? So the electromagnetic field in the near field can comes into interactions with anything that's around the antenna. Okay, any questions so far? Okay, well, okay, great. So, okay, then we move on to the what's called the Touré model, which is a very basic, a very basic approximation on how you can calculate the power of your radio signal at a certain distance from the antenna, assuming very simple model that you have a superposition of direct ray and superposition of a ray reflected from the ground. And because this is actually a wave, we need to face all the consequences of that, meaning that depending on the phase difference between the two signals, we may have the destructive interference when the signal will be minimum, or we can have the constructive interference when the signal will be up to 3 decibels higher than what we expect. Okay, and as you can see, this changes over a distance simply because the phase difference between the two signals also changes. And the idea here is actually very simple. I mean, you take the two component, and if you include the phase, you can calculate all the interference. So it's basically adding two rays together with their complex numbers. So we talk about some phenomena that occur with radio propagation, and we know we have a diffraction. We know we have, of course, reflection that was already mentioned, which also actually depends on the angle of incidence and the medium and polarization. And also with that, we know that all that phenomena can be actually put into the two-ray model. So basically, the two-ray model can be quite easily generalized over multipath propagation. So at the end of the day, you just add to the equation over here, more and more components, and they can correspond to both reflection and diffraction. Of course, this components or rays corresponding to diffraction would have different coefficients here. Also, what you need to take care is here we actually assume that the gain of the transmit and receive antennas is constant over a sphere. However, if you take more and more rays, you need to also take into account variation in the radiation patterns. But overall, the message should be here that the framework is exactly the same. And that gives rise to propagation models that are used, especially with the mobile station-based planning. So here you can see we have a city, which is, a very, very complicated propagation environment with all the buildings, all the metallic structure, all the traffic here. That simply creates enormous amount of different wavefronts, different rays that can be that interfere with each other. Okay. So over here we have the transmitter, which is, let's say, at the top of a building that can be our base station, and we have here a receiver, which is no lower. We can assume this is some sort of a mobile phone. Okay, and basically, as I mentioned, so the received signal will be simply a superposition of all the signals that arrive to the receiver. So again, we know that from the two-ray model, just with more rays, basically. So basically, what is important to remember is that also the reach or complex propagation channel will cause like a significant delays into our signal. We know that the radio signal travels at the speed of light, but because the line of sight component is expected to be always the first one, because it got the shortest way to travel, but it will be followed by multiple signals that are simply reflected. Reflected or coming from any other components. So example could be, that if we have glass walls or a lot of concrete, then we will have, in addition to the line of sight, or actually even we might not have a line of sight, that's a different story, but we'll have additionally some delayed reflected components. we might have some diffraction, what we talked about, right? So here we can see that a signal reaches some peak of the building, and after that it gets diffracted towards our user, and that will be, another components that need to be added to the sum of the signal with certain delay. Okay, and then of course we have the line of sight, which typically is expected to be the strongest and the fastest, simply because it travels direct way. However, in many urban scenarios, we need to actually do communication without line of sight. I mean, if you think about it, if you go around, especially with narrow street, usually your mobile phone wouldn't have direct visual line of sight connection with the base station. So at the end of the day, you might need to rely with only reflected components, especially in dense urban environment. And on top of that, there's some rays scattered by the atmosphere. So we talk here about losses, basically. Okay, so again, what we expect that the radio signal decays with the power 2 of a distance, but in practice, reasons, it can be up to the power 3 or even sometimes power 4 due to the losses in the atmosphere. So basically, we're talking here about small fraction of the radio waves that gets dissipated into heat. Okay. So basically, we had all those phenomena, and you should see by now that this is really a very, very complex scenario. So basically, the received signal is the sum of delayed, attenuated copies of the original transmitted signal. Okay. So basically, also that means that's, I think, one of the questions I got last week, that because of the multiple copies arriving with a delay, what's called your channel response will be stretched in time, right? So it's not as simple as you just get the signal to your phone and that's it. This signal will be kind of a stretched, and usually it may be actually quite challenging to distinguish between different components. So for many cases, you simply cannot say, okay, this is my original signal and the rest are reflected. I mean, you could do that if you have a very wide bandwidth of your signal. Again, going back to the frequency versus time domain phenomena. So if you have signal which is very wideband, then you can analyze that within a very short pulses of time. But hopefully you realize that this is most likely not the case, because most systems we have a very limited bandwidth. Okay, to make things worse, the channel is changing over time. And first of all, because transmitter and receiver may be free to move. Well, for the base station, it may happen, but it's relatively unlikely it will move. Although there are actually some interesting experiments done with the base station that are placed on drones. But well, I would say it's just at least few years until we see those being deployed into commercial cases. However, for the for the mobile phone, it's quite normal that we move, we drive while talking, or well, not even talking, receiving some data onto your GPS would be the case. Here, well, with trains, going up to like 200 or even more kilometers per hour, this basically makes for quite a significant Doppler shift. Okay. Secondly, the environment may change. So this relates to the fact that you have, for example, a train or a lorry that passes by, and in one moment you have a reflection from the lorry, especially if you're close to it, which is basically a huge metallic reflector from from electromagnetic point of view. But then, when the lorry drives away, suddenly your propagation model or propagation channel changes. Another thing is, for example, environmental phenomena. So it starts to rain. Well, this also may, firstly, it may make the concrete surfaces wet, which changes the reflection coefficients. Secondly, of course, rain this is water, so it also can attenuate some signal more than the others. So at the end of the day, this is if you transmit especially a very narrow pulse, you may actually get a different received pulses. Okay. So how to cope with all those things? Well, because of all the varying component, typically we rely in statistical modeling. So rather than modeling deterministically, which can be done for a very specific scenario. However, those scenario, of course, may not be valid if due to the reasons I told earlier. So what's happened is that, generally speaking, the statistical models are preferred. Okay, so basically we assume that there are multiple propagation paths, each with different delay and attenuation. Okay, and basically for most cases we don't really care that much about each individual path. We just know there's plenty of them. We are lazy, we don't want to count them. We just know they exist. And again, what is important that there is different delay and attenuation to them. Furthermore, those are time varying, as you know. So how we can model? Well, we can simply model our channel by having a random sum of k delayed signals with each with individual random delay and attenuation alpha. Okay, so if this is our transmitted signal, so this is real component of the complex number. So SL from T, that's the signal that's the modulated signal we're transmitting. Exponential J2 pi FC times T. So FC, this is our carrier frequency that we're using. And this is basically what would see receiver after on the other side of radio channel. So it's basically a sum of a certain number of rays with randomly drawn amplitudes and randomly drawn time delays. Okay, so basically, so far so good. But of course, the main question is, I said random, but the main question is what statistics do we use? Okay, and so, well, uniform distributions is probably not a good option. That sounds quite trivial, but does anybody think so? The most popular, generally used in science is the Gaussian distribution. We already talked about Gaussian distribution when discussing the noise. Now, do you think Gaussian distribution would work for in this case? For example, to model time delays. So again, let's move on to the chat window, and question to you is, exponential. Well, that may be actually better. Yes. So okay. So right. Okay. So I move on to the yeah. I think that's might be better hint. So first of all, the question actually here is, why do you think Gaussian distribution may or may not be a good idea? So again, you can click likes or whatever under yes or no answer here. And when you make your vote, one vote. Okay, no one else wants to speak? Just try to think about it. I mean, what are the properties, mathematically speaking, of the Gaussian distribution? Okay, 2 votes for no. Okay, so but I think you probably realize that no is the correct answer, right? But the answer that follows is why? And can anyone figure that out? Why Gaussian distribution is not optimum or not the best choice if we're dealing with time, well, basically time events or time delayed events?
Because we have negative values.
Exactly. Okay. Yeah, that's actually simple as that. Mm-hmm. Okay. Right. So sorry. Exactly. So, and of course, you cannot have a negative time delay. All right. So where were we? Okay. So in practical, they are two dominant models of which are typically used for the propagation modeling or for the modeling of propagation channel. So we have what's called Rayleigh from Rayleigh probability distribution and Ricine from the Ricine probability distribution. Each of those, of course, got certain components. Right, I don't want to show you the equation here, but you can easily Google that out even on Wikipedia. But basically, well, what you can see, of course, that both the probability, they just start at 1, and they got, very high probability at the very beginning, which this comes from the fact that our line of sight arrives as the first one. And then the longer the delay means more reflection, which also means the signal will be weaker, just because at each reflection fraction of the power is lost. So the difference is that basically this means the Rayleigh is typically used where we have the case of no dominant line of sight, and that basically and also when the scatterers, so by scatterers we mean any object or any physical thing actually that can either reflect or diffract our radio signals, right? So, for example, building in the context of urban case. The Ricine distribution is typically used when there is a dominant line of sight component. However, However, then there are also additional components, and furthermore, it better reflects the case when the scatterers are clustered. Okay, but by cluster, I mean that the sources of reflections are more or less coming from the same physical direction. So just to give you an example here, if we think about suburban area, so basically we would say about rather part of the city, but that is relatively low with buildings that are maybe 1-2 floors, something more or less similar, let's say, to the I don't know, let's say like a Sempolno or Biskupic districts of Wrocław, right? Which are still a city. However, it's not like the city center or Grunwaldzki Square with no high-rise building. So, which of the two models you think would, or which of the two cases actually would better fit the modeling of that area? Any guesses? Or again, going back to the so again, speaking about the so-called suburban and propagation environment, which of the two you believe would be better? Maybe to simplify, I go back. Sorry. I go back to as a reminder, to the two properties of those probability distributions. So yeah, you can cast your votes now. Okay. So okay, one vote. Any more? Yeah, obviously, well, it's not that obvious since only one person voted. But basically, this is correct answer. So we're talking here about the Ricean distribution. Okay, so again, cluster scatterers means that in general we have a open space propagation, but they're like a group of buildings which generate they generate basically delays or reflections, but they are close to each other. So this is more or less visualized here, right? That typically for Ricean we have a dominant line of sight plus some additional reflections, which, okay, in this case you can see there's one clutter of reflections here, another would be somewhere there, maybe not the best shown. Whereas for Rayleigh, first of all, we get blocked line of sight. Plus, you can see that the reflections are coming from all possible angles. So going back to the question, why this case would be probably more relevant to the city center of Wrocław. Well, apart from the Sky Tower, maybe there's no very high-rise building in Wrocław, but still, you have to bear in mind, of course, that it's all relative, right? In the sense that even though there is no high-rise building, if the base station is at a certain height, we typically on top of the building, it may still experience this phenomena. And also more likely is that this case would be for indoor communication. Okay, so typically, outside of the mobile case, if you think about your Wi-Fi router, and especially in if you have a small apartment or maybe in a student dormitory where there is where the spaces are pretty much close to each other, and the rooms are not too big there, that's what you will experience, situation like that. Now, I know this may be quite a complex topic, but is this more or less clear to everybody? Because I see one or two people having their opinion, or at least trying to make a guess that doesn't look very, very good to me. But okay. In any case, as I mentioned again and again, you can always write me email, or you can always use the consultation time. So just a quick recap, basically, there is, again, more or less the distinction between the Rayleigh finding and the Raytheon finding, which are the probabilistic descriptions of the channel model. There are also more complex model called Nakagami and so on, but that's probably for some more advanced lecture. Okay, so at the end of the day, what I would like you to remember from that is that well, firstly, we have a complex propagation environment which comprise of diffraction, reflections, and as well as attenuation. They can change over time due to Doppler and different movements, or basically change of the scenarios. Next thing is that you can model those environments by approximating each of the wavefront with array and using basically superposition treat. Okay, so if we're speaking about narrowband signals, you can use simply interference and superposition. For wideband signal, you deal with pulses, but still you will experience multiple overlapped signals, and the signal at the receiver is typically the sum of all of them. Again, including the delay or including the phase shifts. And then it doesn't, in most cases, statistical models are preferred. So rather than calculating what will be the attenuation and delay of each of the single model, we just assume some statistical probabilities, and those probabilities are given through Rayleigh and Raytheon probability distributions for time delay. Okay. Now, are there any questions so far? Right. So again, just to summarize all that we've learned on today and mainly on the previous lecture. So just wanted to highlight two kind of model or exemplary propagation environments, right? So one of them, we discussed it already a bit. This is suburban areas. So again, small buildings with so-called cluster pattern and line of sight. Then different scenario will be for the dense urban areas, where the high-rise buildings may block line of sight. And as you can see here, there are some diffractions, multiple reflection, and so on and so forth. And finally, we got indoor environment where you can have really scatterers 360 degrees around you, and also there's like humans moving and some attenuation. So right, okay. So with that, maybe a few more questions. Comparing suburban areas and dense urban areas, which of the two you believe should have, for example, longer delays. So if you're considering, the length of your channel response, which one, for which case this channel response will take longer to basically take all the reflected signals before they decay.
I would say that it would be for the dense urban areas because there are many reflections and the time of each one will be maybe higher than this from the free space.
Yes, exactly right. That's exactly that's the good answer. So basically, there will be more reflections, plus also the lack of dominant line of sight means that there will be greater variation basically between the signals. Whereas for the suburban case, even if we have reflections, we wouldn't normally expect high delays between individual reflections. That's a consequence of the cluttered scatterers, right? That simply, if they are close to each other, they are expected to produce less variation. Okay, and in terms of changing channel and the Doppler shifts or Doppler frequency, so this time let's try to compare the indoor environment with, again, the dense urban areas. So where do you believe we should experience more rapidly changing channel? For which case, basically, the Doppler shift is expected to be more significant. What do you think? So again, comparing, let's say, Wi-Fi to the mobile communication. So you can think about that in two terms, basically. One is the speed of moving objects, which will determine the Doppler frequency shift. And the other, of course, is the signal strength compared to the rest of the reflections. So any ideas, any guesses? Any thoughts on this one?
I think that Wi-Fi is more for short distances and can be more easily attenuated or disturbed from rather than GSM. And but I think that the speed of transmission is better for these short distances for Wi-Fi.
Yes. I mean, obviously that's right. When I'm speaking about yes, that's true. When I was speaking about the speed, I was mentioning the moving objects in the proximity of your transceiver. So again, the problem is that if you have moving objects, you might experience Doppler shift, and that may shift your carrier frequency, or not carrier frequency, but that may shift your signal to a different frequency, which is not really intended for that, right? And then it has consequences, for example, in if you're considering guard frequency, around your carrier for FDMA. So okay, so right. So in general, what you said is true, that the Wi-Fi signal can be much more easily blocked, and in that case, most of the dynamic blockages will be relatively slow, right? Simply because you might have signals blocked or reflected by, let's say, moving humans, your dog, whatever. But typically that moves at a relatively low speed. However, that person might since it's a short range, it's quite close to the transmitter. So a moving person can actually contribute, quite strong reflection. However, since the movement is slow, the frequency shift that can be generated is negligible, right? On the other side, if you think about the city, well, then you can have objects like trains, lorries, cars moving at relatively high speeds, even above 100 kilometers in certain circumstances. So basically, that means that your Doppler shift will be, can be much higher. So your components of your signal may really change rapidly the frequency. Of course, on the other hand, like a moving car will be just a small component of the general reflected signal. So also this is something to take into the consideration that compared to the rest of the channel response, the dynamic factor might be less significant, although they will be subjected to greater speeds. Okay. So that's some general conclusions, and with that we close the topic of the radio propagation and propagation channel. And now basically for something completely different. So, from the world of moving of open propagation with an unbounded region where pretty much everything in the proximity or everything in the environment can cause potent problems, we move now to optical fibers. So basically totally different set of frequency, the optical ones, and also we are dealing in the bounded medium. So the signal is pretty much closed into the cable. So this is basically the outline of this block. And to begin with, let's start with the geometrical optics. So this is pretty much the same what we saw for radio signals. I mean, at the end of the day, the physics doesn't change really. It's still driven by the same Maxwell equations. However, since the frequency is much higher, well, things are calculated slightly different. However, this is just out of convenience, really. It's still the very same equations. So what we have here, we have the optical ray, which hits the boundary between the two materials. Part of that signal gets reflected. Part of that signal goes into the second medium, okay? We have the angle of incidence, angle of reflection. And so in the optical thing, we typically use the index of the material, which is N1 and N2. This is pretty much the same what the permittivity and permeability we saw earlier on for the radio signals, just because of the nature of the light. Usually they are summarized in a single number. Okay. So, and what we want to achieve? Well, we want to achieve that what's called a total internal reflection. Okay, so as you may know, the optical fiber is a medium where the light can travel entirely within the fiber, and it doesn't get out of that medium, so it can be transported over long distances. Okay, and in order to achieve that, we need that the ray of light within the optical fiber gets reflected back into the first medium. So in that case, we want no energy to get into the second medium. We want total internal reflection. Okay, so based on the Snell's law, we know that the reflections is can be guided based on the incident angle θ1 and θ2, so that the N1, which is the material property of the first medium over here, times sine of the θ1, so the angle at which our ray approaches, equals N2, so the second medium, multiplied by the sine of the θ2 angle. Okay, so at the end of the day, we want to build the optical fiber in a way, so it needs to be made out of at least two materials with different indexes N1 and N2, so that we have a total internal reflection. So basically, we want that the angle θ2 is 90 degrees or p half. Okay, why is that? Well, because you can see that if this angle becomes 90 degree, then the ray will simply skew at the interface, at the boundary between the two medium, which pretty much means no part of that wave can enter into the second medium, and we kind of manage to imprison the light within our optical fiber. Okay, and how to do it? Well, this should be quite straightforward. So we knew that we want to have the θ2, so the refractive index being 90 degrees or P2. So we just substitute our θ2 with P2. We reverse. And that's more or less the illustration of what I was saying earlier. So we simply substitute θ2 with 90 degrees. We use the Arcus sine out of those values. And after transformation, we can get the relation that is needed. And what we can see actually, that whether we have or not the total internal reflections does not only depend on the medium that we use. This is actually something that we can engineer and that we can control, but also the light needs to hit the wall at a certain angle. Okay, so this is actually something that is very very important for optical fibers, and that's why very often when you get the laser source, it needs to be injected into the optical fiber at the right angle, which is typically like very, very shallow angle, in order to get this total internal reflections. Okay, so more or less, this is how it is. The optical fiber is realized in practice. We got the core, which pretty much contains all of the or at least most of the signal, with the total internal reflection at the boundary between N1 and N2. And as we know, if it enters the optical fiber at the right angle θ, we can have this phenomena, and the ray can propagate at very high speeds over very long distances. So, any questions so far? Okay, I believe that optical fibers should be already covered by some other lectures that you're having. So what is important to notice is that even though the light enters into the core at the right angle, it can still reflect in different ways, because at the end of the day, it's a cylinder, so some form of a 3D volume, and it will basically have an impact on some of the delays that we have in the optical fiber. So we typically would say about meridional rays and the skew or helical rays. So meridional are basically rays which propagate very close to the core of the optical fiber, and well, basically they would bounce up and down, right? So given the reflections here, this is the shortest or the easiest possible way. So this rays, will travel relatively lower distance than the skew or helical rays. So the skew and helical rays, they would basically, bounce all around the optical fiber cavity. So they would firstly be subjected to reflections at the different angles. And if you look at the light intensity within your fiber, this is more or less what you would see for the two modes, or well, not three modes, sorry, for the two types of rays. So which of those light intensities, one corresponds to the meridional wave and the other to the skew rays or helical rays. Now, which one do you believe is which? Okay, so this might take some 3D imaging, but try to imagine basically the cylinder of the optical fiber, okay? And then try to imagine the two types of the rays. So one goes back and forth, always passing through the center of your optical fiber and reflecting at different points over here. And of course, this is one example that goes up down, but of course you will have more than one ray. So you would have rays that go the same way, just tilted by 90, 25, whatever degrees you name it, okay? And all of them will basically converge or pass through the middle of your optical fiber for that case, for the meridional waves, okay? On the other hand, if you look at the skew or helical waves, they would basically bounce on the outside of the optical fiber. So pretty much the skew or helical waves will rarely go through the middle of your fiber. Okay, so knowing those distinctions, those two properties, again, which of the light intensity you think we have on the left-hand side and which one on the right-hand side?
So meridional rays on the left and helical on the right, because it omits the core.
Exactly, right. So this is just the core, exactly, right. So you can see the dark spot in the center, which basically corresponds that very little electromagnetic energy is transported here, right? Whereas here it's quite the opposite, right? So you can see most of the lighter region, most of the signal is, sorry, most of the energy actually is transmitted through the middle of the optical fiber. Simply it's because the point where all the rays, meridional waves intersect, right? Again, it's the similar analogy as you can see on the meridians on the poles in the geographical context. Right, so this is some reminder about the wave interference. So I hope the concept of wave interference should be quite clear by now. However, the implication goes with the introduction of modes. Okay, so we know that both light and radio waves, they are driven by Maxwell equations. And basically, when we speak about, and those are very, very complex equations. So nowadays we actually rarely almost never calculate them by hand. We got, simulators and computers and a quite expanded set of numerical methods just, to calculate those. However, if we have certain boundary conditions, so boundary condition means that we have certain physical space. It can be either a volumetric or an area. And the boundary of that area has certain limitations. So in the sense, we basically know what happens at the boundary of that area, which is pretty much the case in the optical fiber, right? Because we know that so-called boundary condition is that at the edge of the core and the cladding, we have a total internal reflections, right? So we might not really know what's happened within that core, but the fact that we know the perimeter of the core has this condition imposed, that there is basically no electromagnetic wave coming into the cladding. This limits the possible set of solutions of Maxwell equations. And this is exactly what is called mode in the mathematical context. Okay, we may have many different solutions, each with their own properties. But so basically a mode can be defined as the possible solution of the Maxwell equation, where by solution we mean possible possible distribution of the electromagnetic energy. In this context, this is a light. Okay, so again, we apply the boundary condition at the edges of our region. And then we know that that we are limited by the interference that that was imposed by that was reminded on the previous slide. So, in practical terms, if you add all those conditions together, we know that the phase difference along the perimeter of optical fiber need to be a multiplication of the 2 pi, or the multiplication of 360 degrees. Okay, and why is that? Well, because this is you can trace your point going around the perimeter of your optical fiber. So you start with a certain point, and if your wave kind of goes around the optical fiber and it's end up with 180 degree out of phase, you got a plus and minus sign. So you have basically negative interference. So this is not a possible solution for the Maxwell equation, right? So if you again trace the phase and you get 360 degree, then at that point back, your two electric fields are in phase. We get constructive interference, and such a mode can exist. Okay, now bear in mind, it doesn't tell you, it can be like more than one or more than single multiplication of the full wavelength or the 360 degree of your phase. It can be 3 times, 4 times, and so on, but it has to be always multiplication of 2 pi. Otherwise, we'll have again negative interference, and such a mode would be extinguished. Okay. So this is hopefully to point that out. Now, so far the idea of the modes clear, and the concept of constructive and negative interference within certain closed space. Okay, right. I hope it is. So to move on, this is the example of different modes that we can actually experience in the optical fiber. Okay, so this basically corresponds to the light intensity, but also a phase of your signal. Okay, so basically what you can see here, those are basically like a cut through your optical fiber, and if you can look into the strength of the electromagnetic energy as well as the phase of that signal, this is what you would see for each of the modes. So each of the possible solution to the Maxwell equation. Okay. So in that case, this is basically almost a uniform distribution with pretty much constant phase all over aperture, right? So those modes are typically indexed with 2 numbers here. Well, the 2 numbers simply because we have 2-dimensional space. And since the optical fiber is a cylinder, we index those modes with one number which corresponds to the radial direction, and the other one would be simply the angle over which. So in this case, we can speak about mode 0 and 1. The 0, this is basically the radial component. So basically, if you trace a circle around the radial component, there are no minima or maxima for your mode. So basically, we have pretty much no phase variation, which again satisfies this this constraint, right, of having 2 pi multiplication, because it's simply it's simply the same. It's simply 0 times 2 pi. And also, if you go towards radial, there's again no the index number is simply 1, again simply because that's almost uniform distribution. Then if you move horizontally, we move to the mode 1, 1. So here, as you trace the circle, you can see that your phase changes from 0 to 180 and then back to 360. So basically, the blue color corresponds to the, let's say, negative values. The red color corresponds to the positive values. Okay, so those 2 parts would be out of phase. Then we can go with the higher modes. So here we trace from the red one, which is 0. Then we move on to the 180. Then again, 360, so 0. And basically, we pass twice along the radial dimension through the full phase circle from 0 to 360 degrees, and then back again, hence the number 2. And so on and so forth. You can read that by yourself on different modes. Then the second number, this is the radial, this is the component which goes along the radius. So for example, all those cases, they would have M1. Here we have mode 0, 2. So if we, then we take the second coordinate. If we go from the center of the cylinder to the edge, in that case, we see that we'll have 2 maxima. Okay, so we start with, let's say, 0. Here, our signal will be extinguished, the amplitude. And then we go to the second maximum, which in turn will be the opposite phase. So the M index would be 2. Here, this is the same situation, but with the index number M3. So again, we have 3 maximum, 1, 2, 3. And this is basically pretty much all mix and match, right? So you can have multiple different modes into the optical fiber. And this is basic. It's actually not only applies to the optical fiber, but you can do the same thing at the radio frequencies. In that case, you would experience what's called a waveguide. And in that case, basically your radio signal would be bounded by the metallic or conducting structure of the optical fiber. So pretty much it's simply a pipe with a radio wave inside it, in the case of the waveguide. Okay, now why I mentioned this and why this is important? Simply because all those electromagnetic field probabilities, those modes, they can go, of course, towards infinity, because you can always add more minima or maximum. However, each of these modes require certain minimum frequency because we are still bounded by this requirement of the wavelength. So in the case of mode 0 and 1, this is uniform, right? So typically you just need to satisfy this, so there is, so to say, plenty of space for the electromagnetic signal in the optical fiber, right? However, this mode, if you compare the dimension of your optical fiber to the wavelength, then bear in mind this one goes from 0 to 180 to 360. So your optical fiber need to be at least, half of a wavelength wide in order to support this this wave at a certain frequency. Okay, simply because if it's smaller, okay, you can of course, if you squeeze your wave, well, then you change the frequency. So basically, the message is here. There is a relation between the size of your optical fiber and the frequency over which the mode will be excited. Okay, and the general rule is that the more higher order modes you have, the larger optical fiber you need. Okay, simply because, again, for the case of the, let's say here mode m equal 0,3, right? You change phase from 0 to 360 and back 3 times, right? So again, you need at least 1.5 wavelength of diameter of your optical fiber to support this electromagnetic signal. Is that so far clear to everybody, or at least to most of you? Okay. All right. So this drives us to the distinction between single mode and multi-mode optical fiber. Right. So typically, the single mode is the optical fiber that can transmit, only single mode, whereas the multi-mode optical fiber will typically transmit multiple modes. And typically, when you say single mode fiber, we typically mean the fundamental mode. Okay, so single mode fibers, they would have significantly slower diameter as compared to the multi-mode fibers. And I hope after the previous slide, it should be quite clear why this is the case. Simply because if you have a very narrow fiber, you got only the space for the fundamental mode to propagate. Whereas for multi-mode fibers, it's much more larger, and we can see that the difference is, in the factor 10 approximately, right? What's also important that the single mode optical fiber, it will transmit only the basic fundamental mode. Why? Well, because that's the easiest one to excite. I mean, typically there are a few exceptions to that, but generally, if your op fiber can support higher order mode, it can also support the lower mode, simply because the requirements are satisfied. And yeah, so any questions here? All right. Then we briefly move on to the manufacturing. So basically, well, in order to get the material of certain refractive index, there is basically a certain preform, which again, with material properties that are engineered, as well, of course, as the preform, the material need to be transparent, because the refractive index is one thing, but obviously we don't want to get any impurities or any attenuation basically into our material. And then in order to get a very thin optical fiber, the preform would be simply gravitationally stretched or maintained down with a stream. So there is a certain weight applied, and that's how you, the process shown here, how you stretch your optical fiber from the preform. And then interesting thing is also the splicing of the optical fiber. So this is basically an equivalent of soldering. If it's typically done by very specific machines which apply heat to connect the two fibers. And of course, the trick is that it needs to be smooth, because as you should know by now, any discontinuity will cause a fraction of the waves to reflect back to the source of the signal. Okay, and of course then the core and the cladding is one thing, but for mechanical reasons, typically we need some additional protective layers. So basically, you got coating, outer jacket, and so on, but those are purely for protection. They're not used to transmit the signal. And then also very often, of course, the optical fibers, simply because this is 50 micrometers, we typically put a bunch of those optical fibers together, simply out of convenience. Right. So this is how optical fiber link works. And again, you should see this is pretty much mapped the very same scheme that we talked from lecture, 1, or actually lecture 2. So we start with the input, we got coder, we sometimes called converted in the context. Then we have the light source, which in that case would act as our modulator. So it will alter, again, the amplitude or phase of the light signals, or less often actually in this context, frequency. Then we have the source to fiber interference. This was, of course, not included in the generic telecommunication model, but this is because of what we talked today, that in order for the laser light to enter into the optical fiber, there need to be certain conditions, such as the proper angle. Then over here we have the optical fiber cable, which in that case, that would be our channel. And that's typically quite a good channel, really. Okay, so even though there always will be certain noise added in the channel, per distance, in the case of optical cable, that noise would be relatively minimum, or definitely lower, of course, than compared to the radio communication. And then on the receiver side, well, again, you got the interference to extract the light from the fiber optic into our detector. Then we have the detector, which acts here as demodulator. And then from the light pulses, we get the decoder, which again goes back to the information that we want to extract. So again, this is the very same scheme that we talked from the beginning of our lecture, just with some specific components added that are specific to the optical fiber communication. Okay. And just a brief mention about the diode. So the electronics here, this is basically just an example of how an optical laser diode can look, that is injected into the optical fiber. Then this is an example of the modulator, where we can change amplitude and phase of the light of our light signals. And interestingly, actually here we can see there's the radio frequency input. And this radio frequency input, it's actually in this context, it's in the range of the gigahertz. But here actually it's considered as the low frequency modulating signal. Okay, so simply because the rate, it's compared to the optical fiber, which is in the terahertz region, this is basically the low frequency, and then it allows to modulate the light pretty much using the same quadrature amplitude modulation that we already discussed. So again, that's a universal concept. And then we have, of course, the light detectors, which again, transmit the light signals into electric signals. Okay. So far so good. Now apart from our systems, we also have to deal with some attenuation that is present in the optical fibers. And basically, those are some example of the attenuation of the visible light compared to the wavelength. And what we basically see, we have some peaks based on the, some atmospheric phenomena. So it's definitely not a uniform. Okay, and for to ensure low attenuation, which allows our signal to travel over larger distance, there are typically used 3 transmission windows, which, as you can see here, the second and third, they're actually located in the range where there is a low attenuation here. The first one is located at somehow shorter wavelengths, but this is a little bit due to due to historical reasons. Okay. So that's it. And then another interesting phenomena. So in the optical fiber, we very often will have what's called chromatic dispersion. Okay, and again, the physical phenomena here is actually very same to what we experienced or what we discussed earlier on with radio channel propagation. However, here, of course, we are, in this, as I mentioned, nice bounded region. So we don't have random scatterers and so on. However, we have quite a lot of reflections which will alter our signal. So what will often happen, and this is called the chromatic dispersion, that's one type of dispersion, is that when we enter a short pulse into our optical fiber, well, you should all know now that a very short pulse in time domain will consist of multiple frequencies. And as it, of course, passes in the optical fiber, the problem is that the properties of the material will slightly change with the frequency. Okay, so it's basically very difficult to make a stable, to make the material with stable and constant refractive number over a large set of frequencies. And those changes are typically very small. However, if you think that the signals are subjected over tens of kilometers, sometimes, they get basically accumulated. Okay, and those small changes will cause that different components or different fractions of this very short, what was originally very short pulse, will travel at different speeds, will be delayed differently, and that will, at the end of the day, it will make what's called pulse spreading. So at the output of your signal, your pulse will be much wider than the original pulse that you've inputted into the optical fiber. Okay? And this is, of course, something that needs to be taken into consideration. Simply because if you want to transmit, multiple pulses very consecutive next to each other, which will guarantee high speed of communication, then you risk that those pulses might merge into each other. Okay, and then you won't be able to distinguish between them. Okay. And then another type of dispersion is what's called modal dispersion. And well, you know now the concept of the mode. And basically what you expect, what you saw is that also different modes can well, they do propagate with slightly different speeds. Okay, this got to do with the fact that each of the modes will have the maximum and minima of the amplitude of the wave at slightly different location. Okay, so again, in this case, those differences are very small, but if you think about it, they get accumulated over very large distances. Okay, so at the end of the day, the model dispersion will have the similar effect as they may stretch your pulse and make your signal much longer than the inputted one. Okay. Right. So, are there any questions so far here? Okay. So with that, we can move on to our last concept for today. So there is quite an important distinction between the core and access networks that I wanted to highlight here. And the reason is that typically actually the core networks is the main application of the optical fiber. And historically also the oldest one. So typically when we have the large telecommunication systems or network, we speak about the core network, which are basically the networks joining large hubs or large centers, which are connected with the high capacity link. So typically those will be connection between different routing sites, between different server farms of Google or any company really. Okay, so typically those will be links that are stretched over large distances with very high capacity, but relatively few branches. Okay, and they are designed to get large volumes of communication across the continent, across the country, or even globally. Okay, so that's the big scale. However, it does not solve the problem of getting the signal to users, right? Because obviously, if you have a good connection to the university, and that's fine, right? But you want to stretch it towards your private home or individual offices, and this is typically what is done with access network. Okay, so access network is the part of the network which provides direct service to users. So it's basically the fact which goes from the big routing center somewhere out there into individual homes. Okay, and those are typically much more heterogeneous. So by heterogeneous, I mean using different technology, ranging from Wi-Fi through mobile data, through classical copper wire, for example, also optical fibers, and it will have a lot of branches. Each branch is terminating, in individual's office. However, of course, the capacity in terms of telecommunication signal of each of those branches doesn't need to be, as large as in the case of the core networks. Okay. And with that, the last so-called last mile problem. So in the context of access networks, this is basically like a historical evolution of the concept of fiber to the home. Right. So initially, you could see that the first one was basically fiber to the curb, which basically this is at the time when optical fibers were very complicated to handle. It's not even the matter of the fact that the cables themselves were expensive, right? However, transmitting the signal as an optical light was not processed very well, right? So initially, very often when you had to do routing over your optical fiber, you had to transfer that from optical to the electrical one, direct, route it to the proper way, and then transfer back using laser diode into the grid. So that was the challenge back then. So typically the fiber was delivered only to a street cabinets, from which the exiting copper lines would be used as the last mile problem, right? As the final part of the access network, basically. Okay, and then as you see here, over the time, recent advances in processing optical technology allowed us actually that obviously currently we're in this stage, so we can have a optical fiber even quite at your direct home or apartment. And an important part of this development was so-called passive optical networks. Okay, and the fact that it is passive is a crucial here, simply because it doesn't need amplification. It's maintenance or anything like that. Okay, it's completely passive optical. It's completely passive network. Okay, so how does it work? Well, your signal is simply passively divided into the individual homes. Okay. And I would say that actually those are some frequency bands, but I don't think that's that much relevant. So I think with that, we can conclude our today's lecture. Again, is everything clear, or are there any questions? Okay. Right. So So I believe that was quite a lot of material for today. So hopefully it was understandable. Anyway, thank you very much for attending this lecture. Have a nice weekend, and see you next week. Again, remember, if you're interested, you're more than welcome to register for the lecture or webinar on the 12th of May. And also, I will be having the consultation time if you need to ask anything. So thank you very much.
Thank you.
Thank you, and goodbye.
Thank you. Bye.
Goodbye. Thank you. Goodbye.
Bye.